So good afternoon. So today I want to continue with like consequences of time dilation and length contraction. If you remember last time we considered like muon lifetime, which is like created in the atmosphere, and how we make sense of the observation from the muon lifetime in compared to observation in the laboratory. And another physical, observable, and widely used effect of relativity is relativistic Doppler effect. So I think everybody is familiar with the Doppler effect. Sometimes we call Doppler shift. Like sometimes you hear like an ambulance. The ambulance passes in front of your house. When it's approaching, it has like a certain pitch. As soon as it passes from your house, it changes the pitch, right? And it gets further and further away, or it gets closer and closer to you. The sound you hear changes. So maybe I can, Doppler effect, I can first write the Doppler effect. Let me call it classical Doppler effect, which is non-relativistic Doppler effect. Like the frequency is something like this. Frequency, the source frequency, 1 plus V. Let me first write, and then I'll explain what these things are. So here, V naught is the frequency of the source, the ambulance frequency, if you want. And nu naught is the ambulance frequency, and nu is the frequency you hear. So this V is observer speed, and this uppercase V is source speed. And a little remark that we need to be aware immediately is whether the observer or source moves seems to matter, right? Like what we said in the principle of relativity. Whether you move or I move doesn't matter, right? All inertial frames are fine, and everything has to be mutual. And whether you choose my frame or your frame shouldn't matter. But here it seems like there is like a difference, right? Whether source moves or observer moves, they seem to enter the equation in an asymmetric way. How do we reconcile this? Is that okay, or is there a problem we need to consider here? Yes? Oh, yeah, thank you. I forgot to mention. So this is the speed of sound. If you want, it is like a wave speed. Like, for example, the speed of sound, depending on the pressure and temperature, is like about something like 300 meters per second. And it is like a property of medium. So how do we make sense of principle of relativity in this equation? Is everything fine? Yes?
In this part, because of there is an inertial reference frame.
Yes. Right. What is that inertial reference frame?
Air.
Yes, air, right? So there is like ether in this case. There is like an absolute gas, if you want, or like in the case of water, there's like a stationary water. So there is an absolute reference frame. So we are fine with that. But in the case of relativity, that's not the case. In the case of relativity, it should not be like that, and we are going to formulate, or if you want, we are going to reformulate it. We didn't drive this because we are not going to use it, but we are going to drive the relativistic version of the Doppler effect. And the Doppler effect of light is different because there is no ether. So let me first consider the simplest one. So this is transverse Doppler. Let me like draw like an exaggerated source. So this is source, and the source is I don't know, giving light, and the observer, let me call this red dot, is the observer, and suppose observer is moving with velocity v. And the source has like a frequency nu, and if you want, nu s is the source frequency, and nu o is the observer frequency, and our job is to find nu o, observer frequency, in terms of source frequency and the velocity, and of course the velocity of light. So this one is very simple because the only difference between red moving observer and the source, which is stationary according to us, is the time dilation, right? There is nothing else, because motion is perpendicular to this wave propagation. We don't have to deal with length contraction rate. We only need to account time dilation, and that's it. Let me try to write there with their notation. So T naught is ticks in S source frame, and T is ticks in observer frame. But what is going to happen is the ticks in source frame is going to shift with respect to observer, right? Observer will see, so observer T is going to be T naught times 1 minus V squared over C squared. So that's observer. So this is source. I think I shouldn't have changed my notation. Now I want to write this like 1 over T is equal to 1 over T naught 1 minus V squared over C squared. And for 1 over T, I'm going to write nu. This is nu naught. So this is observer frequency. This is observed, and this is source. And since 1 minus V over C, this entire thing is less than, right? This is less than 1. V naught times something less than 1 is less than 1. Then we are going to see nu is less than nu naught. Is that correct? Observed frequency is always lower than the source frequency. Good. Observed frequency is less than source. So this is observed. So this is source. Okay, I think now we are good. So let me just put these colors, and I want to introduce the terminology. So the colors, so this is red, orange, yellow, green, and blue, and violet. And wavelength for red, it is like 700 nanometers, and for violet it is 400 nanometers. And here is lambda decrease, right? Lambda decrease if you go to the right, whereas frequency is 1 over lambda, right? C is equal to nu times lambda. We are going to come to that. So the frequency, so nu increase if you go towards red. But you can see the I think it still doesn't make sense. It should be blue shifted, it should be red shift, but it is like, so observed frequency is always lower. Yes, like, yeah, I think, did I say decrease? So it is, I say decrease and I write increase, and I read increase and I get confused. So this is decrease. Okay, now everything makes sense. Since frequency is decreasing, when you go towards red, right? red is like decreasing frequency side, we are going to call this redshift. Okay, now everything makes sense. Because I know it's supposed to redshift. That's the important terminology to keep in your head. Good? Any questions or comments? Yes? Okay. So this one was the easy one, but I messed up badly. But let me try to do the second one and see if we can get a better. So now I want to do the receding. Let's do receding Doppler. So we have still, again, let me just draw the picture. So there's like a source, and there's some wave emanating from the source, something like that. And in the receding Doppler, you are moving away from the source. So this is v, this is the velocity. So what we need to do is like we need to consider like two wavefronts. So let me consider a wavefront like this. And this is like, I want to call this point A and this point B. And observer is here, observer. And so for observer to see the full periods, so observer should first receive A, and when observer receives B, observer will say he or she saw the full frequency. And what this means is like, let me just copy this. So first, this is the full period, right? But by the time the B arrives the location of observer, observer will also move just a little bit. Maybe, I don't know, something like this. So there has to be like a little bit additional time, additional distance needs to be covered. Right? So this entire thing is in full wavelength, and maybe I can try to write it a little bit better. So this thing is full wavelength, and there is a little bit additional, what did I call it? Let me call this velocity times Ts. Good. And how much does it take? So the total distance, so B is moving with the speed of light. The total the total time in the source frame is going to be the wavelength plus additional distance V times Ts, and you need to divide this entire thing with the speed of light. And Ts is going to be, okay, you can solve this for, okay, what I am going to do is, this is 1 minus V over C. I take that side, and it is going to be lambda over C. And this is what I'm going to call 1 over nu source. But lastly, I need to convert this to observer frame, like convert to observer time. And this is going to be T observer times 1 over 1 minus V squared over C squared. Now let's collect everything. And for T observer, I'm going to write this like, maybe I can write it like this. Let me actually not do that. So for T observer, I'm going to write 1 over nu observer. Then 1 over new observer, 1 over 1 minus v squared over c squared. So I just wrote Ts, and 1 minus v over c should be equal to 1 over new source. Good. And lastly, new observed is going to be equal to new source. This one I'm going to write it like this. So this is, let me first write and like eliminate. So this is v over c, and this is 1. Okay, I'll write this like 1 over v over c, 1 plus v over c, and cancel this and put 1/2 here. This is going to be vs 1 minus v over c divided by 1 plus v over c, and take the square root of entire thing. Yes?
Could you use another notation for the velocity?
Yes, let me use f here. I think you are right. This is, let me put f for frequency, right? I had this experience before, I forget, sorry about that. So this is f, and this is source. And I want to write, yeah, this is observed, this is, and yeah, this is the final one. Okay. Now let's calculate if it's like red shift or blue shift. 1 minus v over c is something less than 1, and you take the square root, so this is going to decrease source frequency. And 1 plus v over c, but this is 1 over, this is also going to decrease. Then f observed, right, f observed is going to be less than f source. And this is exactly like before, this is going to be redshift. Good. Any questions? Like the last one is approaching Doppler. Yes? So here, yes. So first,
to the second calculation, how did we think about
let me repeat, and you can ask one more time. So first I said in the source frame, right? This entire equation is in the source frame. I said how much it takes between the times A is received by observer and B is received by observer, right? Like you are moving, I'm looking at you, and you receive A, and I start my clock, and you keep moving, and then you receive B, and I stop my clock. That's what I'm trying to calculate. And for this, I need to calculate first the full wavelength, right? This is like the time that full wavelength is taken. And then there's additional time. In my frame, you are going to be moving with velocity v, and in my frame, you'll go a time distance like ts. Then ts, the time, is going to be total length divided by speed of light, and I solve this for ts. But now is the point, like, so this is my frame, this is the source frame, but we say that we need to convert this time to observer time, because observer is in a different frame, and we are trying to decide what observer will see. To convert from source frame to observer frame, we just use the usual time dilation formula. Ts is going to be T observer times, right? And then after that, everything is basically solved. Whenever I see T obs, I put 1 over F obs. Whenever I see Ts, I put 1 over Fs. And let me also fix this. This is F. This is also F. And once you solve it for Fs, we found the redshift. I generally get these things wrong, but I know the result. Redshift, if something is moving away from you, it should be redshifted. I know this one, and I try to fix my calculation like this. So approaching Doppler, so let me just give you the result, because it's very simple once you did this confusing calculation. All you need to do, if something is approaching to you, this red V should be minus V, right? You just flip the velocity. Then here what you are going to see is this is going to be plus, and this is going to be minus. And exactly like what we calculated, this is going to be F observed is going to be bigger than F source, and this is going to be blue shift. Okay. Okay.
Hocam, I have also a question.
Yes.
about transverse calculation.
Yes.
You wrote T equals to T naught over square root 1
Mhm.
minus B squared over C squared
Uh-huh.
in the upper part.
Yes.
Yes, this effect is mutual, but we wrote at the first class T observer equals to T source over this again.
Yes.
But in this case, we want to find frequencies, but source is at the rest, but observer is moving.
Yes.
We did different type, T not equal
Yes.
to T over. Actually, the names are different.
Yeah. I think I don't want to change the name because I'm going to mess up. But the logic is as follows. First, let's think about the time. The observer's time is observer is receiving the light, and what observer cares is how much time passes between two fronts, right? Observer is looking, right? The first front came to me, and I'm waiting for the second front, but the source is going to decide that second emission by its own clock, right? So T naught passed in the source frame, and the second front is emitted. But now we need to convert this to observer frame. So observer is going to see a delay between these two emissions, right? So the first peak is emitted, and then until the second peak, there's like a time difference. The observer who is receiving the light is going to see a delay in time.
But while thinking this, let's think about in rest frame 1 second passed, while in observer's frame 0.5 seconds left, and we create plane waves. Observer sees the first plane waves upper part and the others. In rest frame, person can say 1 second passed and 1 wave passed.
Yes.
And for the observer, it's only 0.5 seconds left. And that's why, in my opinion, moving observers should experience like 2F frequencies.
No, I think, so that's why we are writing it like this, right? There's like a wavefront, and all of these wavefronts are moving, like they are like synchronized. There's the one frequency, and so there's like two peaks, one peak here and one peak there, and maybe I can also write observer here. And now, so this observer received the first peak, and it doesn't matter where, right? There will always be like a second peak reaching to this point. Then observer should only wait enough time so that the second peak comes to here. But second peak comes to here in the source frame when the time difference is enough, right? This T naught passes. When T naught passes, this peak is going to reach here. And that's the frequency in the source frame. Now we are saying that, okay, I received the source, but because of the frame difference, there has to be a delay, right? There has to be a time dilation. I need to account that, and this is where I account that. So it's a little bit confusing, you are right, but I think this is correct, because I checked the book, right? And I know it has to be a red shift, so you need to find a way to convince yourself. Good. Now here is like the application, and then we can take a break. Like kind of like your question about like excitation, right? We look at these distant stars, right? And these distant stars are sending us like light waves all the time. And typically these light waves are going to have like frequency components, and we are going to spend a really long time to understand these frequency components. And main frequency will be due to generally hydrogen, because that's the most abundant atom in the universe, and it has like a characteristic emission. And I know like wherever I look, I need to see the signature of hydrogen, right? And I look, I think Andromeda is not a good one, because that's not what it does. What I look at like some galaxy, faraway galaxy, and the frequency, there's like some frequency for hydrogen, and I see it to be redshifted. Okay, this is, let me change the color. Redshifted just a little bit. I don't know, some delta nu. So what does it mean? So the frequency is a little bit shifted to the left. And from our analysis of Doppler, what can I say about that galaxy, right? I know where the hydrogen line should be, but it is just a little bit shifted. This galaxy, either the hydrogen in that galaxy is different, right? Maybe there's like a different laws of physics in that galaxy. Hydrogen works in a different way, which would be nonsense. Or we can say laws of physics are universal. Hydrogen here is the same as hydrogen there. So it has to be in the same frequency, but it is shifted. How do I explain the shift? Yes? No, not expanding. Yet I'm saying something simpler. Yeah, it is moving away from you, right? So that's the first piece. And now, like, okay, so this is this is going to tell you galaxy is moving away. So there are some, I think Andromeda is the one that's blue shifted, but it's approaching to us. But almost like all galaxies we observe seem to be moving away from us. So suppose this is you, and you look at here, some galaxy, it is like redshift. You look at here, some galaxy, it is a redshift. You look at here, so this is you, and this is redshift, this is redshift, this is redshift, this is redshift. So what can you tell? Wherever you look, everything is redshifting. What does that mean? Not expand, yeah, it's now, yeah. Now it's expanding, yes. Everything is moving away from you, right? It is like expanding. So now is one more piece, a little bit more surprise. What people found actually, like, suppose you look at another galaxy, there are ways to determine how far the galaxy is from you, which doesn't concern us. But if it is a little bit, if the distance is a little bit bigger, the red shift seems to be increasing, right? Like you look at the galaxy, let's say you look at galaxy in Istanbul, it is like red shifted, and you look at another galaxy in Edirne, it is red shifted even more. What does it mean? Right? So not only the universe is expanding, it's like everywhere is like, it's kind of like a balloon, right? The further away from you, the galaxy, the faster it is going, right? And that's, yes?
John, it might be a bit more general as a question, but how do we know that the redshift we're detecting is the superposing of something else?
How do we know?
That the redshift we're detecting is the superposing with another wave.
Because there is like, there is no other way, right? Like when you look at a spectrum, you know the spectrum, right? Like when you look at outside, there are like a finite number of things can come to you. It can come from hydrogen, and hydrogen has like special levels. It can come from like lithium. It can come from sodium. It can come from more complicated atoms. And we know all of these, right? This is characteristic. There is no line in the emission spectrum that overlaps. It's characteristic. And the slot for hydrogen is only for hydrogen. There is nothing else can take place of. We are going to see that. That's the power of quantum mechanics. That's why we are so sure about these things. Because quantum mechanics 100% tells us what is supposed to be there at that emission line. And if it's shifted, we have to find another explanation. In that case, it's the Doppler shift. Okay? So maybe I can take a break here and then continue in second half.